Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your SumamMiss. My channel name is also SumamMiss. You can watch my videos on my channel. If you found useful, please don't forget to like, share, comment and subscribe. Your comments are highly valuable. The topic for today's discussion is buoyancy. It is a common experience that an object feels to be lighter in liquid than in air. This observation suggests that the liquid exerts a force on the body when it is immersed in a liquid. So this upward force which tends to lift the body is called buoyant force. So let me explain this with an example. Consider a flat plate of thickness T and area A. It is immersed in a liquid of density ρf parallel to the free surface. The area of the plate at the top and bottom surface is A and it is kept at a distance of h from the free surface. So thickness of this plate is T. We have learned previously that pressure at any point in static mass of fluid depends upon its position with respect to the free surface and specific weight of the liquid. So the pressure force that is acting in the downward direction on the top surface of the plate equal to ρf into gh into A. So ρf gh is the intensity of the pressure and A is the area of the plate. Similarly, the pressure force which is acting in the upward direction on the bottom face of this plate equal to ρf into G into H plus T into A. The net force is in the upward direction. So net upward force equal to the difference of these two forces, that is equal to ρf into G into T into A. So this is buoyant force and it is denoted by Fp. So in this equation, A into T represents the volume of the plate and ρf into G represents specific weight of the liquid. So ρf into G into T into A represents weight of the displaced liquid by the plate. Or in other words, buoyant force Fb acting on the plate equal to weight of the liquid displaced by the plate. So the point of action of this buoyant force is called center of buoyancy. So for a floating body, buoyant force that is equal to the weight of the liquid displaced by the body and it acts through a point coinciding with the centroid of the displaced volume. So this is known as Archimedes principle. So weight of the floating body that is equal to weight of the liquid displaced by the body and it is acting through the centroid of the displaced volume. So centroid of the displaced volume that is called center of buoyancy and it is indicated by CB or B. Though this relation is developed for a simple geometry, it is valid for any body regardless of its shape. So when a solid body dropped into a liquid, upthrust which is acting in the upward direction, it is also called buoyant force which is equal to the weight of the liquid displaced by the body. So buoyant force is also called force of buoyancy or upthrust. So when a solid body dropped into a liquid, it will float or it will remain at rest at any position in the fluid or it will sink. The submerged volume fraction of the floating body equal to the ratio of the average density of this floating body to the density of the fluid. If ρ is the density of the floating body and ρf is the density of the fluid, if ρ is less than ρf, the body will float. If ρ equal to ρf, the floating body will remain in submerged state, whereas if ρ is greater than ρf, the floating body will sink. Now let us discuss about the equilibrium of the floating body. So a floating body is concerned, the weight of the floating body that is acting downward, whereas buoyant force that is acting in the upward direction And if the floating body is in equilibrium, these two forces are in line. So the point through which the buoyant force acts, that is called center of buoyancy. For any floating body, weight of the center floating body that is equal to the weight of the displaced liquid, or it is equal to weight of the liquid corresponding to the volume of submerged portion of the floating body. So weight of the floating body that is equal to mg, that is equal to Fp. Fp means the buoyant force, that is equal to weight of the displaced liquid. If Vb is the submerged portion of the floating body, so Vb into specific weight of the liquid will give you the buoyant force. So if you are equating this weight of the floating body equal to the buoyant force, then volume of the submerged portion of the floating body equal to m by rho f. The important application of buoyancy concept is the assessment of stability in the case of submerged and immersed body with no external attachment. It is of great importance in the design of ships and submarines. The stability of the floating body can be explained by the concept of the ball on the floor analogy. Figure shows 3 balls on the floor. Consider the case A. So here, when we move the ball to the right or left, it will return to its initial position. This is because a restoring force developed due to gravity will return the ball to its initial position. So that means the ball is in stable equilibrium. In the case B, when we move the ball to the right or left, it would stay put at its new position. It does not show any tendency to return to its initial position, nor it move away from the existing position. So in this case, this ball is neutrally stable. In the case C, the ball is rest at this moment, but if it is disturbed, however small the disturbance may be, the ball will roll. It won't show any tendency to come back to its original position, rather it diverges. Here the ball is unstable. So the stability of the floating body can be explained by considering this situation. In this figure, the floating body is under equilibrium. Weight of the floating body that is acting downward through the center of gravity, whereas buoyant force that is acting upward through the center of buoyancy. Both forces are in line. So that means the floating body is in equilibrium. So if you are giving a small tilt to this body, so there is no change to the weight of the floating body. It is still acting through the center of gravity, but due to the alteration in the shape of the displaced volume, center of buoyancy is, which is the centroid of the displaced volume, is changed from B to B1. So buoyant force is now acting through B1. So if you are drawing a vertical through B1, it will cut the axis joining the center of gravity and the old center of buoyancy at a point M, that is called metacenter. M is metacenter and GM is metacenter height. The distance moved by the center of buoyancy, that is BB1, equal to x. So BB1 equal to GM tan theta, and if theta is very small, then we can write x equal to GM theta. So in this tilted condition, the metacenter is above the center of gravity. So if M is above G, the righting moment W GM theta is developed, which will try to bring back this floating body to the stable equilibrium condition, and GM is positive. But if the floating body is tilted in this manner, there is no change in the position of the center of gravity, but due to the change in the shape of the displaced volume, center of buoyancy is now changed to B1. And if you are drawing the vertical through B1, it will cut the axis joining the center of gravity and old center of buoyancy at a point M, that is called the metacenter. So in this case, the position of the metacenter is below the position of center of gravity. So if M is below G, an overturning moment W GM theta is developed, and that moment added to the tilting action, so that will lead to unstable equilibrium. So in this case, GM is negative. But if M coincides with G, body is in neutral equilibrium. However, Stability of the submerged body and immersed body depends upon the position of the center of gravity with respect to B. In this figure, weight of the submerged body that is acting down through the center of gravity, whereas buoyant force that is acting upward through the center of buoyancy. So in the tilted condition, both forces are not in line. So due to this angular displacement, that is W bg tan theta or W bg theta is a righting moment because center of gravity is below the center of buoyancy. So it will bring back the body to its equilibrium condition. Whereas in this figure, center of gravity G is above center of buoyancy. So the moment developed is an overturning moment. So it will lead to the unstable equilibrium conditions. But in the case of fully immersed body, there is no change in the displaced volume. So rotational stability of the immersed body can be explained by considering the position of G with respect to B. So the immersed body is under stable equilibrium if center of gravity is directly below B. So that is possible if the body is bottom heavy. In that case, center of gravity is directly below B. So if the center of gravity is directly below B, it will develop a restoring moment. It will return the body to the stable position. So that is why in the case of submarines, the engines and cabins for the crew to be located at the lower half in order to shift the weight to the bottom. If G is directly above B, in this case, any disturbance will cause this immersed body to turn upside down. So it is under unstable conditions. When G is coinciding with B, it is neutrally stable. However, in some situations, G and B are not vertically aligned. So in that case, it would rotate to the stable condition without any disturbance. So here, G and B both are not in line. So in this case, a restoring moment is developed in the counterclockwise direction. So this body, it would rotate to the stable state without any disturbance. So we had enough discussion regarding the theoretical concept of buoyancy, stability of floating bodies, submerged bodies and immersed bodies. For the time being, it is enough. Thank you.